Leetcode problem 2581, count number of possible root nodes. So for this example, let me try to explain it. Yeah, because here the drawing is not so good, so I put it inside slides. So let's just understand it from here. Yeah, so for this question, actually, we are giving a graph, but it is a tree structure. I mean, for each of the node, it can become the root of the tree. We just need to count how many combinations that meet the condition. So the condition is that, let me just use a pen. Yeah, so the condition is that we just need to find how many tuples. So the tuple gonna be from the parent to the child. So for example, this is 0, 1, 1, 3, 1, 2, and 2, 4. And we are also have a guess set. And inside the guess set, it's gonna be an array of tuples. Yeah, so if the parent child is inside the guess set, so we're gonna plus a 1. So if all the values is less than and equal to k, so this means we're gonna update the final result. It's gonna be updated to 1. And for this example, so for example, inside the guess set, maybe we have I don't know what is that, but let's just use an example. Maybe inside the guess set we have like 1, 3. We also have like 1, 2, and we also have like 0, 1. Yeah, so this is just the guess set. Yeah, we have 3 tuples. Now, for the parent child, if the root is 0, so for example 0, 1, we have it, and for 1, 3, we also have it. Yeah, and for 1 to 2, we also have it. So the number of them are going to be on 3 because 2 and 4 is not inside. So the k is also equal to 3, and 3 is less than or equal to k, so this is a valid count. But what if the root is 1? So the thing is going to be different. Yeah. So if the root is 1, so 1, 3 is still inside. 1 to 2 is this one still inside. But 1 to 0 is not inside because the sequence is always from the parent to the child. It means 1 to 0 is not inside, so the count is going to be 2. So this is not a valid count. Yeah, so this is just my example. I think it is not the same as the example in the question before, but basically this is the idea. So this means we're gonna check all the root. So the root can be any nodes from 0 to 4 in this example. So if we solve it like the brute force, it's gonna be O(n squared time. Yeah, but for such problem, we cannot use O(n squared time. We have to solve it like using O(n time or n log n time. So the easiest way to solve this problem is by using the DP or trace method. So the DP or trace method is basically we're gonna solve it by using the DFS. We just need to run 2 DFS. So the first DFS is that we're gonna start from this root 0, and we're gonna count it how many valid count. So for this example, it's gonna be 3, 0, 1, 1, 2, 1, 3. So the valid count gonna be 3. And the next step, we will not repeat the same process again and again. Otherwise, it's gonna be O(n squared. We just need to use the change root method. We just need to change the 2 root. Basically, we're gonna call it reroot. It means the root is gonna be starting from 0 currently, but for the next step, the root is gonna become 1. So if the root is 1, what happens? Yeah, we need to see some patterns for this problem. So if the root is 1, so what happens to this node 1? And yeah, so what happens to the node 1 to 2? It is still 1 to 2, right? You see, 1 to 2. Here is still 1 to 2. We didn't change the sequence, so the parent child is still 1 to 2. What about 1 to 3? So it is still 1 to 3. We didn't change anything about the sequence. It means our count didn't change. So what about 2 to 4? We didn't change the relative sequence of 2 to 4, so this is 2 to 4, and here is also 2 to 4. So what actually changes is only 2 nodes, from 0 to 1. So this is from 0 to 1. Now what happens? Yeah, now it happens from 1 to 0. So this is the only change. So if we can find some formula or find a pattern according to this change, basically we've already solved the problem. Yeah. So what actually happens? So from the beginning, from the root 0, we have a count of 3. Now, what happens is that we just need to check if 0, 1 is inside the guess set. So 0, 1 is inside. So this means for the next change of the root from 0 to 1, we're gonna need to minus 1. Because before 0, 1 is inside. Now, after we change the root, we don't have this 0, 1 tuple. Yeah. So it means we're gonna minus 1. Now we need to check if 1, 0 is inside or not. So 1, 0 is not inside. So it means we're gonna plus a 0. Yeah. So if 1, 0 inside the set, so we're gonna plus a 1. So this is the idea. So after changing the root, what's gonna be the final result? So it's gonna be 2. 3 minus 1 plus 0, it's gonna be 2. Yeah, so this is the idea. So after one operation, what is the time? It is just O1 time. So first running of the DFS, we're gonna use ON time. But after that, we just use a reroot for reroot from 0 to from 0 to 1, 1 to 2, 1 to 3, 2 to 4. So for each of them, it's gonna be O1 time. So in total, it's gonna be another ON time. Yeah. So the time complexity gonna become ON plus ON. So this is why it is so fast. Normally for such problem, we don't need to analyze like 0, 1, 1 to 2. We don't need to analyze all of them. We just need to analyze one position from 0 to 1, what happens. Because for others, it's exactly the same. Yeah. Because from 0 to 1, 1 to 2, 1 to 3, or 2 to 4, it's exactly the same. We just need to run another DFS. Yeah. So if you understand the basic principle of the BPO trace problem or the basic principle of the reroot method, now we can start coding. So let me just start coding from here. We are giving this kind of as is, so we're gonna turn this as is into a graph. So I'm gonna prepare a default list, and inside it's gonna be list, and then we're gonna check all the as is. So it's gonna be the as is, and we just need to prepare an undirected graph. So here gonna be v, and gv gonna append the u. So this is the adjacency list graph. And secondly, we need to turn this gases into a set. So let me just use gases. It's going to be the set of gases. So inside, because the gases is an array, we need to turn it into a tuple, and then it's going to be the set. So uv for uv inside the gases. So in this way, we turn this gases array, nested array, to a tuple. So now the gas is going to be a set. Yeah. First of all, we're going to run DFS, but before that, let's just prepare a count. So this count is just for the root node starting from 0. So from the beginning, it's going to be 0, and then we're going to call a DFS to calculate what is the count for this 0. So in this example, the count is going to be 3, because there are 3 edges that meet the condition, like 1, 3, 0, 1, and 2, 4. So all of them is inside the gases set. Yeah. So we're going to run DFS to calculate it, and after that, we just need to run the reroot function. So basically, we need two functions. So one is a basic DFS, another one is a reroot. Basically, they are nearly the same. It's just a very basic of DFS function to check the how many count. So first of all, let's just check this count. So inside it's gonna be an x and parent, and after that we're gonna call this DFS. So the DFS is gonna be starting from node 0, and the parent is gonna be a -1. So let's just finish writing the basic pattern. So for y in gx, if y is not equal to the parent with the y and x. So this is the basic pattern. Or we can just copy the basic pattern from here, because it's exactly the same. So for the reroot function, it's going to be the same. So we just need to use another name. Maybe I'm going to call it reroot. Yeah. So now let's just finish the first function for this DFS to check the count for this root 0. So we're going to start from the root 0, and next we're going to check this node 1. So if 1 is not equal to the parent, this means the parent is -1 from beginning, so this one is not equal to the parent. So this means for our DFS, so for the DFS it's going to be 1. So for the DFS it's going to be 1 to 0. Yeah. So from the beginning it is 0 to 1, and after that, yeah, it's going to be a 1 to 0, but this is okay. But for us, we just need to count how many of xy. So the xy just means from the parent to the child. So how many like xy, like 0, 1, 1 to 2, 1 to 3, and 2 to 4. So we just need to count it from here. So if x and y inside the guesses set, so it means we find a count. So we're going to update the self.count, going to plus equal to 1. Yeah. So let me make a comment from here, and let's just finish the checking. Let me return a random 0. Let's just call this DFS 0 minus 1. So we just need to check this self.count. So this count is just for the node 0. So how many count? So normally it should be 3. Let's just check that. So the count is 0. It means it is not okay. Let me just check. Yeah, let me just print xy from here, and we can find what is wrong with it. So I have 0, 1, 2 to 4, 1 to 3. It seems everything is okay. Yeah, 0 to 1, 2 to 4, 1 to 3. Yeah, it seems everything is okay. But what is my count? I didn't check the count. Let me just print out the self.count after call the DFS, so we should understand what does that mean. Yeah. So now, as you can see, the final count is going to be 3, and we find 3 tuples that is inside the guesses set. So it seems everything should be okay. Yeah. So now let me just delete the print. Yeah. So up to now, from here, we are just checking the count for this root 0, and we're going to run on DFS to check how many of them. So 0, 1, 1, 3, 1, 2, and 2, 4 if it is inside the guesses set. So we're going to update the self.count. And secondly, we're going to run the reroot function, and we're going to use this self.count starting from the root 0. And now we're going to start the reroot function because the root is going to change from 0 to 1. Yeah. And here, we just need to be careful that we just need to find the tuples from the parent to the child, not the child to the parent, because x is the parent and y is the child. So this is the parent. So currently, we are running the DFS. So this is the parent from x, and this y, this x is the parent of y. That is why we're going to use xy tuple, because this is a parent-child tuple. So if you understand from here, so everything should be okay. Let's just run another reroot function to finish it. So before that, we're going to prepare a self.result. It's going to be starting from 0. And finally, we're going to return self.result. Now for this reroot function, what we're going to do, we're going to pass a parameter. So we're going to call this reroot function first. And similarly, it's going to be 0 minus 1. 0 is the node 0, and minus 1 is the parent, or you can set a minus 2. If it is not equal to 0, not equal to all those nodes, definitely it is okay. Or you can set a negative infinity or infinity. Everything should be okay. Or you can set a none. I mean, everything should be okay. It always depended on, or you're right. If the parent not equal to child, definitely it is okay. And for the reroot function, we're going to pass a self.count, because this is what we need in our formula while we're calculating the count if we change the root from 0 to 1. Now let's just check it from where we need to check it. So inside, I'm going to prepare a count. And now this is the parent x, y is the child of x. Yeah. So while we are running the function, we're gonna start from this node 0, and then we're gonna do the reroot. So from the beginning, it is like 0, 1. Now after we do the reroot function, it's gonna be 1 to 0. So the code gonna be changed according to my formula before. So the code gonna minus a tuple of x, y inside the guesses set, and it's gonna plus a tuple of yx. So if this yx, I mean 1 to 0 is inside the tuple or not. So yx inside the guesses. So this is the only formula. The formula is not so difficult, I think. If we did some reroot problems, or if we did some DP or trace problem, definitely this is not so difficult to find. Basically, we need to find this kind of a formula to solve the problem. Yeah. So from the x, y, it means 0 to 1. If it is inside the guesses set, so we're gonna minus a 1. So before it is inside, we're gonna minus 1. And now it's gonna change to 1 to 0. So if 1 to 0 is inside the guesses set, let's check. So 1, 0 is still inside the guesses set. It means the code gonna minus 1 and plus 1. So it's gonna be a 3 if the root is 1. And similarly, from the root 1 to 2, we're gonna use the same formula to calculate. And after that, it's gonna be 2 to 4, or 1 to 0, 1 to 3, and we can finish the check. But how can we update the self.result? We can update it from here. So if the count is more than and equal to k, so we're gonna update the self.result. Gonna plus equal to 1. So after call the reroot function, we can directly return the self.result. Now let me just run it to have a check. Now as you can see, it works. Now let me just submit it. Yeah, as you can see, it's pretty fast, and it passed all testing cases, and the time complexity is just O(n), and the space complexity is O(n). And let's just check. So the number of n is 10 to the power 5. This means we cannot solve it by using O(n) square. That is why we're going to use the DP method. So this is a DP or trace method, and specifically it is called reroot and DP or trace problem. We just need to swap to a root node for each of the step. So the first DFS will be similar to the second DFS, second reroot function. We just need to find from where we need to call to the final result, from where we need to update the reroot. So it is the same pattern for most of the reroot problem. I think that's all for it. Thank you for watching. See you next time.